Greetings. Welcome to week 3 of algorithms and data structures. Let's go ahead and jump right on in. This week we're going to be talking about hashing queues and heaps and how those are basically formed in C++. So our week learning objectives, let's go ahead and make this a little bigger. So we're looking at week 3 learning outcomes. We want to explain and have you be able to explain your hash tables and hashing functions in C++, implement rehashing and handle collisions. Collisions, we'll be talking about what that is. Implement queues and priority queues. Okay, implement heaps and understand their operations. Use the SQL, the standard template language, standard template library, using those queues to create priority queues and other unordered containers. And again, if you just keep in mind what we're talking about when we talk about data structures are containers. Where do we put information? Okay. So we've gone so far and looked at we're introducing a new container each week as to how and what we can put in those containers in order to solve our problem. Excuse me. Okay, so week 3 at a glance. Okay, hash tables store data using a key and a hash function for fast access. Rehash. Resize the table when the load factor, gets too high. And queues. FIFO structure for ordered processing of data, and then priority queues and heaps, accessing the highest or lowest priority elements efficiently. So when we're putting stuff in a queue or a heap, we want to be able to say, give me the lowest one, okay, and to be able to do that quickly. So with that, we have certain criteria we have to meet and how we store that information in order to make that an efficient operation. Okay. Now, here on number 4 are basically the basic structure of a hash table. We have a key associated with each record, okay? What we do is we take that key and we're going to basically run it through a hash function. Okay, so the hash function here is we're hashing the key. In this particular case, our function is key %7, which says, I want you to put this at the location it corresponds to the remainder of the key %7. So in this case, if my key was 6, I would go into 7 one time with a remainder of 1. So it would go into the hash table. Now with this particular example, I'll kind of I put it out there that what is not shown here is what the key of Alice, Bob, Carol, Dave, and Eve is. Okay, so beware that what is actually going into the hash function is the key that corresponds to that particular record, and not the alphabet or lettering themselves that are running through that hash function. But basically what it's saying is that once I do hash that key, it's going to put the records into a unique location, not necessarily in the sequence that you brought them in. They will go into the hash table based on the key that's associated with that particular record. Okay, a collision. Okay, so I have a record. I take its key, I run it through the hash function, and it gives me a position that I need to put the record in the hash table. Yeah, no problem, no big deal. But what happens when the next key that I bring in has the same hash location? That is called a collision. When we have two keys that hash to the same caching location, that is a collision that has to be resolved. So collision example, here we have key %5. Okay, here it happens to be that we're saying that Bob hashed to position 2 and also Tom hashed to position 2 based on the key that was associated with their particular record. Okay, so here's some common resolution techniques. What happens when I have a collision? Okay, the first one here is separate chaining. Store all items that hash into the same index into a linked list. That's similar to what we're showing here. Bob hashed first, Then came in Tom. They both had the same hash key. So I'm going to chain Bob and Tom. Now, I'm doing this chaining because I have to remember that I'm storing something in the hash location. I'm going to come back around and have to read that information. So I'm going to be reading that information by taking the hash key, hashing it through the hash function, getting a location, and then I'm going to go to the location to read the record that has that particular hash key. Okay. So if I have a collision, what that linked list is going to do is say, okay, once I get to that hash key, I in essence have to sequentially search that linked list in order to find the record that corresponds to the one I'm looking for, to the key that I'm looking for. So that's what's being explained here. Separate chaining. Store all items that hash into the same index in a linked list. This other way we can handle that particular collision or a collision is to probe for the next available slot, linear programming, quadratic probing, etc. So here's what it's saying is that when I get a particular key, I hash it and I go to and it puts the stuff in the hash table. I get another one and I get a collision. What I'm going to do is, rather than putting it in a linked list, what I'm going to do is I'm going to find the next available open slot in the table. And I'm going to put that record in that open slot. So when I'm reading the record, and in essence going to do the hashing, find out that what I hashed doesn't contain the key that I want. So I'm just going to sequentially read down through the table until I find my record. Okay, not really doing any kind of linked list. We're just reading down through the hash table because where I would have put it is the first available slot that was open in the hash table. That's open addressing. And then rehashing. Okay, increase the table size and then reinsert all elements. This is a little bit more expensive, but what it says is, okay, let's increase the size of the table so the likelihood that I'm going to have a collision lessens. And so again, here I have to redo the whole table. I got to rehash everything. It may be worth it for me to do that. It may not. Okay. So we need to determine, based on our resolution techniques, what is the most efficient way for me to handle if I have two records hashing to the same hash location. That's explained here. Good hashing functions distribute keys uniformly and reduce collisions. That's the kind of hashing function we want. Okay, vocabulary terms, going to highlight. Hash table, a data structure that stores key value pairs using a hash function. The hash function itself is a function that converts a key into an index and in the hash table. Okay. Collision, when two different keys hash to the same index or same location. Load factor, the ratio of the number of elements in the table size. Okay. The ratio of the number of elements to the table size. And so if I have the number of elements that I possibly can possibly have is 10. Okay. And my hash table is 11. Okay. That particular situation is saying that I have a high load factor, very high load factor. The higher the load factor, the more probability that I'm going to hash to a collision. I'm going to get a collision. Okay. So we want that ratio load factor to be small, and the way we make it small is we make the table that we're putting it to large. There's less likelihood that a particular key is going to hash to the same function or have the same index. Okay, so rehashing, process resizing the table and resetting all elements. We talked about this is basically, and my table is 11. I have a bad load factor. I want to double that load factor so I can increase my table to 20. Okay, and then I'm going to rehash everything. Okay, and that should reduce my my loading just from that rehashing. Okay, why does this matter? Okay, search engines use hashing. A lot of the things that you'll see that you're searching for something will basically use a hashing function and hashing key. E-commerce systems, scheduling systems, social networks, real-time analytics, all of these applications basically are heavily dependent on using a hashing function type implementation. Everyday examples. A library catalog uses a hash table to quickly find the books by ISB number, ISB number. Okay. A queue, people waiting in line are served in the order that they arrived. That's using a queue. A priority queue, emergency room. Patients are seen based on the urgency priority. So I go to the hospital, I got 5 people in front of me, but my need is greater than their need. So they'll basically take that information and bump me up to the top of the queue. And that's a priority. So if there's a priority for a particular record to come in front of all the others, and that's when we would use a priority queue. Okay. Again, how we determine what that priority is up to us as far as what is the key criteria that we're going to be looking at to determine whether one record should have a higher priority than the next. And then a heap, okay, a tournament ranking system keeps the highest score at the top. Okay, so this is a heap. It's more similar to a priority queue, but when we add records, we make sure that the top of the heap contains the most important record. That's kind of explaining here. Okay, hopefully you can see this. Okay, if not, when you print it off, you look at it on your own PC, you should be squared away. But here, just unordered map. This is the C++ example for an unordered map. The C++, we're building a queue. Here we're building a priority queue, and here we're building a heap. And so this is the C++ implementation on how we can implement those particular structures. Okay. Okay, again, you'll be seeing these again. Your research on how you want C++ to create your particular container. Okay, we'll have these particular codes that you can fall back on and basically use these, put these in your library of things. This is, I'm going to do a priority queue. Okay, how do I do it? Okay, you have this information. This is how I create the queue, and I push and pull. Okay, or say for a priority queue. Code walkthrough, just kind of walking through, get used to this again, because again, the code that you give me, okay, as I said, I want you every line to explain what that particular line is doing. Okay, so in this particular example, code walkthrough, hash insert. Okay, here I'm taking a hash and I'm hashing an integer key. Integer means it's got to be numeric. Okay, can't have an alphanumeric value that I'm hashing. And what I'm going to return here is the key percent table size. Okay, so whatever my table size is, my table size was 20. Then I'm going to take the key and I'm going to do a key percent 20. If my table size, and remember, this is talking about the load factor. Okay, my load factor is that value that I want to make sure are evenly spaced out, so that the probability that I'm going to get a collision is less as my load factor gets bigger. Okay, so here we're doing an insert. We have the key and the value. So we go here, we're indexing the hash key. Okay, then for some glasses here, man. Okay, so then we're creating the index, and the index is equal to when we're hashing the key. Okay, then we're basically putting that into the table. Okay, auto %p equal table index, we're putting it into the hash table. And we're basically looking at this and saying, table 7 bucket, hash function make key to the index, 7 through 8, if the key exists, update with the value, otherwise insert it in the end of the list. Okay. And I notice that what we're doing here is if we get a collision, we're going to go to the back of the table, and that's where we're going to start putting it. Okay. We may put it, in the first open slot, or we may tell the system that if I get a collision, move it to the back of the line. Okay. Okay, so that's what's happening here. And there's other strategies. And what we're giving here is the basic structure of a key. We hash it, we put it in the hash table, we got a collision. How do we resolve it? There's several ways we can resolve that collision. Okay. So this is kind of highlighting that this is one of many cases that I can use to highlight a collision resolution. Okay, so here are common mistakes that the students make. Poor hash function, okay, causes many collisions and degrades performance. Maybe cause a load factor, and it just may be because that the function that you're using is a bad hashing function. Okay. If you're forgetting to rehash, load factor gets too high, leading to slow operations. Okay, a lot of collisions, a lot of resolutions we got to do. And again, keep in mind, the more collisions I have, okay, the longer it's going to take me to read the record once I want to read it, okay, is because I have to go through all other records that also have the same hash function location or index. So that's where it's saying here, how did it slow down? It slowed down because how I'm handling collisions. Wrong queue type, using stack when FIFO is required or vice versa. Need to look at which particular container you're using and whether that makes sense, okay, based on what your requirement is and what your goal is. Okay, heap confusion, forgetting that a heap is a complete binary tree, okay. We talked about a binary tree. You'll be doing some research. Remember I told you that what I want you to do, if you look at something and you don't quite understand it, look it up. Okay. Look it up. Now, if once you look it up, you still don't understand it, then that's coming to me and then we'll walk through it together. Okay. But my expectation from you is that with anything that you don't understand, you'll take that next step and you'll look up that information for your satisfaction. Okay, knowledge check. Things I want you to kind of look up and put in the back of your mind that you should know. What is the purpose of a hash function? How is collisions handled in separate chaining? What does rehashing accomplish? What is the difference between queue and a priority queue? And what is the top element of the heap? If I have not already done so, and I'm kind of putting this in past tense, I will probably have some pop quizzes. Okay. So when you come in on a Thursday, I will give you a pop quiz. If you're not there, okay, then you don't get any credit for that pop quiz, and then that's a ding against you. So every Thursday when you come in, be prepared to take a pop quiz that basically consists of a knowledge check. Okay. And I'll kind of bring them into class, the first class we have that you most likely be given a pop quiz at the beginning of each class that kind of outlines what you should have read or what you should have seen as far as online looking at the video. Kind of tells me that, yeah, you actually did look at the video. So beware, that is going to happen. Okay. So there we go. That's it for hashing functions, another type of container for week 3. We'll put this in our list of ways we can store information. And again, looking at how that is accomplished in C++. And then we'll go kind of highlighting some of the other things here. Fast access and order processing lead to better performance. STL provides powerful containers that simplify implementation. Hashing provides an average of 0.1. Remember, 0.1 is the fastest. 0.1 says I can get it in one access. Okay. Understand the behavior before choosing the structure. That's what I've been saying all along. Understand what you're trying to do before you determine what kind of structure you're going to put that data in. Pause the video for your understanding. We're pausing until we see each other on Thursday. Okay, everyone, have a good one. And let me know if any questions or concern. in taking this and doing your first step for your homeworks, quizzes, and project. And for those who are online for your discussion questions. Everybody have a good one. Bye.